Welcome back, students. Today we are going to go into the mathematics behind state functions, and we're going to see what we can do with these state functions. Last time we got a lot of work out of solving problems with ideal gases. We were able to figure out the internal energy, the enthalpy, the work, and the heat, but not all systems are ideal gases. For example, some gases don't behave ideally, and some substances aren't gases. If we want to describe the internal energy and enthalpy of solids, liquids, more complex gases, we need more mathematical tools, and we can't use the ideal gas law, obviously, for systems in which it doesn't apply. What we're going to do today is focus on how the internal energy changes, and we'll see enthalpy next time, how these changes as a function of pressure, temperature, and volume. What we'll do today is go over the exact differential of internal energy. This is going to be a concept you want to be familiar with and understand why we're doing. We'll go through all those reasons and we'll talk about it more in class as well. So the learning goals for today are going to be able to evaluate partial and total differentials, as well as exact differentials for state functions. We're going to see a couple of terms, beta and kappa, that are used to describe these state functions. These are terms that come in when we don't assume the ideal gas law. We'll see what those are. And at the end, we're going to evaluate what the internal energy is and why, and we're going to want to explain why it's fair to assume that the internal energy only changes as a function of temperature, which is what we did in the last lecture. Today, we're going to be all on the whiteboard. We have a lot of math to do, so let's go ahead and get going. We'll begin the lecture by considering how pressure changes. For the purposes of this lecture, we are going to assume that the number of moles is constant. That's not something we have to do. We can throw that in there as well, but it makes things a little bit easier. And that's going to be the case if we just have a gas that's being compressed and expanded. If there's no new gas being added, no chemical reaction, the number of moles is constant. So if it's constant, we'll just assume that it's 1 here for these purposes. And what we can say is, well, what happens to the pressure? We know that our ideal gas law says that PV equals nRT. So that means P is equal to nRT over V. If N is constant and R is constant, the variables that we have are the temperature and the volume. So what we can say, and the way we'll write this, you hopefully have seen this before in math, is that P is a function of V and T. That is, if the volume or the temperature changes, so does the pressure. And the way we can write this is that P is a function of V and T, and that function is nRT over V. If we assume that N is equal to 1, we would have RT over V. So we have this relationship between temperature, volume, and pressure. We could, of course, also come up with other expressions. We could say something like V is a function of P and T, and that function would end up being RT over P, and we could do the same for T as well. So we could say that T is a function of V and P, and that T is equal to PV over R if we wanted. And all of this is assuming that N is equal to 1. Now, knowing this, we might want to describe how the pressure changes. So if we increase the temperature, what happens to the pressure? We've done a little bit of this before, and before we've been assuming that we're changing the temperature only and not the volume. So if we change the temperature and not the volume, what happens to the pressure? Well, we can see by this relationship here that P is equal to RT over V. So if T increases by 2, P will increase by 2. But that's not true for non-ideal gases. So in general, how do we do this? We're going to treat this as if it is a function. So let's go through a simple function example of how we would do this. Let's consider the function f of x is equal to 3x plus 1. And we want to know how f changes as a function of x. Now, it's pretty obvious for us here that it's a line with a slope of 3. So if x increases from 1 to 2, f will increase by 3. But let's go through the math, because for our complex state functions for things like solids and liquids and real gases, we won't always have an equation that we can actually evaluate. So how could we do this? If I have a scenario where x begins at 0 and changes to 3, I want to know how much my f changes when x goes from 0 to 3. Now, one thing I could do is simply evaluate f of 0 and say f of 0 equals 1, and then evaluate f of 3 and say f of 3 is equal to 10. So the difference there, so delta f would be f of 3 minus f of 0, which is equal to 10 minus 1, which is equal to 9. So when x changes by 3, f changes by 9. And I can do that because I have the function. Now, what if I don't have the function? There's another way that we can actually solve this problem. And what we're going to do is the following. We are going to say that delta f is equal to the change in f with respect to x times the extent of x change. Now, what is this? In this case, what we're doing is we're saying that delta f over delta x, right? We're talking about the derivative of f with respect to x. And we'll find this derivative specifically at x equals 3, where we are changing. Now, in this case, it's a line, so it's the same everywhere, but for more complex functions, that's not the case. And then instead of having a delta x, we'll have a dx. So when we see this kind of language, we can write df is equal to df dx multiplied by dx. And what we're doing is we're saying, what is the rate of change of f with x? And then dx here is going to be the extent of the change. So if I do this, what is my df dx? Well, if f of x is 3 x plus 1, df dx is simply equal to 3. So my df here is equal to df dx, which is 3, times dx, the extent of my change, which is x is going from 0 to 3, which is 3, and I get an answer of 9. So I get the same answer that I did before when I consider it in this way. Now, for simple lines, this might seem like it's more work. We just plug in our numbers. And if we have a nice function, it is often easier to simply plug in the numbers. But like I said before, for things like liquids and solids, we don't have real equations that describe those. But what we can do is measure the rate of change with one variable with respect to another and get an estimate for this slope here. And if our extent of change is relatively small, the rate of change should be approximately linear. So a simple slope is often good enough to figure out the total change. The next question that we'll want to consider, especially looking at our ideal gas law, is that up here we have P as a function of V and T. We don't just have P as a function of V or T. So if only pressure, if only volume changes, if only temperature changes, we should be able to relatively easily figure out what's happening to the pressure. But what if the volume and the temperature change for the pressure? So let's think about an example of standing at the top of a hill and moving down the hill. So you're standing at the top of some three-dimensional hill and you move down this hill. Let me attempt to draw a three-dimensional hill here. So we have a hill, and then try to imagine that we have another kind of slope off in this distance coming down towards us. So if we're standing at the top of the hill and we take a step to the right, we will go down a certain amount. And if we take a step forward, we will go down a different amount. So what happens if I take a step to the right and a step down? How much far down have I actually gone? What we're going to do in this case is evaluate the exact differential of df. So what we're going to do is an extension of what we just did before. We are going to say df, in this case, the height that we have, is equal to the following. It is going to be equal to the partial derivative of f with respect to x at constant y, times dx, plus the partial derivative of f with respect to y at constant x dy. Now, again, we have what seems to be pretty complex math notation, but it actually is the exact same thing that we've seen before. So what we're saying here, our df is the total change in f. So how far down have we gone? In this case, f is the z dimension. How far down have we gone? df dx at constant y is how far do I change when I go in the x direction. So in this case, if this is the x direction on my hill, the df dx is simply this slope here. This is my partial derivative of f with respect to x at constant y. And in the same way, the slope in this direction is the partial derivative of f with respect to y at constant x. And then my dx and dy terms here are simply the extent of the change. So what I'm really doing is I want to say, well, how far down do I go? And then my df dx at constant y is each step to the right takes me down, say, 1 foot, then this would be -1, and then dx would be how many steps did I take down to the right. So if I took 2 steps, this would be 2. And then if my every step forward takes me down 2 feet, my df dx, or my df dy would be -2. And if I took 3 steps that way, I would put a 3 in here. I'd add these together, and I would get -2 plus -6 equals -8. And I would say I have gone down 8 feet when I took 2 steps to the right and 3 steps down. So that's what we'll be doing with our state functions. We'll start with pressure, and then we'll go to internal energy today. So what do we do for pressure? Well, for pressure, we know that pressure is a function of temperature and volume. So we can say that dP is equal to the partial derivative of pressure with respect to temperature at constant volume times dt, the extent of the temperature change, plus the partial derivative of pressure with respect to volume at constant temperature times dV, the extent of the volume change. For ideal gases, we have an equation for this. So we know that P equals RT over V, again, assuming N is equal to 1 mole. So we can evaluate dP dt at constant V. If we took the temperature derivative of this, we simply get R over V. And then we have dt. And then if we take the volume derivative of this, we get minus RT over V squared dV. And this is an expression that relates how the pressure changes as a function of temperature and volume. If we wanted to know how this changed, we would simply need to integrate this expression, talk about the actual change from initial temperature to final temperature and initial volume to final volume. When we have these differentials of state functions, and this is something that we're going to be seeing a lot over the next few weeks of class, so you really want to get down what they mean. I know that they can look very, arbitrary and can be somewhat confusing with all of these letters. We're doing math with letters and not numbers anymore. But they simply are talking about the extent of change and the amount of change. So how do we change as a function of temperature, and then how much does the temperature change? There's a couple of properties that will come in handy in the future as we go through evaluating these expressions. The first one is that for state functions, if we take one partial derivative followed by another, that's the same as if we did the second one followed by the first. So what I mean by that is that the partial derivative of respect to temperature, and I'm using temperature and pressure and volume, we could use any variables here. So the partial derivative with respect to temperature at constant volume of the partial derivative of pressure with respect to volume at constant temperature is equal to the partial derivative of volume at constant temperature, and then we do the partial derivative of pressure with respect to temperature at constant volume. So these two things are the same. It doesn't matter which order we take the derivative in. This should be hopefully somewhat familiar to you. From last year, we didn't do partial derivatives, but we did things like take derivatives of see commutating of operators, is a similar sort of thing here. And we'll see how we can apply this later. So just keep this in the back of your brain for now. Another useful rule is we can divide by these things. So we can take the partial derivative of, here I'm using x, y, and z, but we could also use p, v, and t. So if we have the partial derivative of x with respect to y at constant z, this is equal to 1 over the partial derivative of y with respect to x at constant z. So we can see the way that this will come up is if we want to move one of these from one side of the equation to another, we can divide the equation by this and get this, flip it around basically, if you bring it to the other side of the equation. The final rule that we'll use is called the cyclic rule. So these three rules are all going to be useful to remember as we go forward, and they're to keep in your mind as we work through derivations in the lectures and in class. So we can also say that if we have a multivariable function, so we have a function with three variables, we can say the partial derivative of x with respect to y at constant z times the partial derivative of y with respect to z at constant x times the partial derivative of z with respect to x at constant y is equal to -1. And so here, note that we have xyz in the numerator, xyz in the denominator, and xyz in the subscript. So we're having basically every way we can talk about this change here, and it's equal to -1. We have seen that since we have an equation of state for ideal gases, we can evaluate the partial derivatives. For real gases and for other things, other phases of matter, such as solids or liquids, we don't have perfect equations of state. To determine how the pressure changes, we rely on experimentally measured constants that are unique for each gas. The constants we'll use are denoted beta and kappa, where beta is the volumetric thermal expansion coefficient and kappa is the isothermal compressibility. So we have a lot of words here, but essentially what we'll say is that beta is equal to 1 over the volume times the partial derivative of volume with respect to temperature at constant pressure. And kappa is -1 over the volume times the partial derivative of volume with respect to pressure at constant temperature. So with these two terms, we can put these together to figure out how dP changes. So what we're going to do, and we'll see this in class, is we're going to take this expression up here, where we had an expression for dP in terms of dP dt and dP dV. Oops, sorry about that. And we are going to rewrite this in terms of beta and kappa. And we'll do this using these two rules especially. So we'll say that our dP ends up being equal to beta over kappa dt and -1 over kappa volume dV. And so with these numbers, we'll see some examples in the book or also in class, is we can figure out how pressure changes for real gases as a function of temperature and volume. If we actually wanted to calculate these changes, we simply need to integrate this expression. So an actual delta P would be equal to beta over kappa delta T -1 over kappa times the natural log of V final over V initial. And beta and kappa are constants that experimentally measured. You can just look them up if we wanted to figure out the extent of a pressure change. What we're going to do next is try to figure out how the internal energy changes. Now, the internal energy of an ideal gas is going to be subject to the three parameters of the ideal gas, namely pressure, temperature, and volume. However, those three variables are related. So we do not need to say that our internal energy is a function of temperature, pressure, and volume, because if we describe internal energy as a function of temperature and pressure, we've already incorporated the volume component as well, because the system only changes in 2 out of those 3 ways. So if we know how the temperature and pressure has changed, we also know how the volume has changed. So that being said, our internal energy is only a 2 variable function. It turns out that it's easiest for us to measure the internal energy with respect to temperature and volume changes. So our internal energy is going to be a function of temperature and volume. We've already seen how it's a function of temperature. In this lecture, we'll see how it's a function of volume as well. So if we want to know the differential for U, the exact differential, our du is simply equal to, just like we've done before, the partial derivative of U with respect to temperature at constant volume, dt, plus the partial derivative of U with respect to volume at constant temperature, dV. And what we need to do is figure out what these partial derivatives are, because we don't have a nice equation of state for internal energy. We only have these nebulous terms. We've already seen how internal energy changes at constant volume. If we have constant volume, we don't need to look at this term because dV equals 0. And we know that at constant volume, our du is simply equal to d Q, the heat of the process, and that is equal to NCVM dt. So if we want to get a delta U, we need to integrate our differential here, and we end up with delta U is equal to the integral of NCVM dt. Like we said in class, in most cases, it's okay to assume that CVM is not a function of temperature. In some cases, that's not appropriate, and you actually have to integrate an approximate function that, again, comes from experimental measurements. But if it is appropriate, which it is in most cases, we get that delta U is equal to NCVM delta T. Now, how does the internal energy change with volume? We've been thinking about ideal gases up until now, and we've talked about in class the assumptions that go into the ideal gas law. The two assumptions are that ideal gases are non-interacting and that they are point masses. So if we have a system of non-interacting point masses and we change the volume of that system, the energy doesn't actually change at all. The energy would come from intermolecular interactions. The ideal gas doesn't interact. We don't change the interactions by compressing them together or expanding them. And so what we've seen before when thinking about ideal gases is that if we had a constant temperature process, delta U is equal to 0, meaning even though the volume is changing, the internal energy doesn't change. That's not going to be the case for real gases because real gases are not non-interacting point masses. They do interact. There's some sort of van der Waals interactions that they can have. In some cases, there might be polar interactions that they can have. And they will eventually do things like form liquids. And they also don't want to be in the same spot because they are actual real molecules. I'll give you an expression for how the internal energy changes as a function of volume. We will derive this expression later. We need to discuss entropy to do that. So once we start discussing entropy in chapter 5, we'll be able to derive this expression. So we'll say that du dv at constant t is equal to t times dp dt at constant v, and then minus p. And this is called the internal pressure. How does this work for our ideal gas law? Let's attempt to evaluate it for an ideal gas. So for an ideal gas, du dv at constant t is equal to the temperature times the pressure, the derivative of pressure with respect to temperature at constant volume. Remember, our pressure is equal to nRT over V. So a derivative of pressure with respect to temperature at constant volume simply gives us nR over V, and then we're subtracting the pressure. In this case, we have nRT over V minus P. And remember that P is also equal to nRT over V. So in this case, du dV at constant T is equal to 0, just like we expect for an ideal gas. For non-ideal gases, this will not be the case, and we will get some non-zero number here. To put these things back together, we can say that our exact differential of internal energy, du, which we initially wrote was du dt at constant v dt plus du dv at constant t dv, is now equal to cv dt plus, I'll put this in brackets here, t times dp dt at constant v minus p dv. Now, why have we actually done this? It may seem like we've replaced a partial derivative with a second partial derivative. So we started with du dv at constant t and ended up with dp dt at constant v, which might not seem any easier. But remember, we can relate our dp dt at constant v to our volumetric thermal expansion coefficient and our isothermal compressibility. So we can also say that du is equal to cv dt plus t times beta over kappa, these constants that we can look up for any gas, minus the pressure times dv. So it is a little bit easier to consider in this way for real gases. As we see here, the internal energy is technically a function of temperature and volume. But for an ideal gas, the volume dependence ends up being 0. Since most gases behave like ideal gases under most situations, it turns out that it's usually appropriate to assume that the internal energy is only changing as a function of temperature. This is going to be true for any gases that are under normal conditions. And what I mean by normal conditions are basically standard temperature and pressure. So if you take a gas and you cool it way down, it might not obey the ideal gas law anymore. And this would make sense because cold gases eventually become liquids. The same thing would be true for high pressure scenarios where high pressure gases also become liquids. So if we're at cold temperatures or high pressures, the ideal gas law kind of starts to break down, but at otherwise normal conditions, all gases usually obey the ideal gas law. Next time, we're going to look into the exact differential for enthalpy. So we've done internal energy today, we'll do enthalpy next time. And we'll also use this to see how real gases behave as we change the volume.